to the OSI and TCP/IP model section of the Network Fundamentals course for the Juniper JNCIA. Let's move along here and have a look at the actual models. So whether you're in a wired or wireless network, data communications today happen by the way of packets of information traveling over one or more networks. But before these networks can work together though, they must use a common protocol or set of rules for transmitting and receiving these packets of data. Many protocols have been developed over the years. One of the most widely used is the Transmission Control Protocol, which is this one here, and this one is an older version, and also a generic protocol known as the OSI model or the Open System Interconnection model, which is of course this one here. Let's have a little look at the 7 layers of the OSI model. As you can see, we have layer 1, which is the physical layer, which is here. The protocol data unit is known as a bit, and this is where the electrical signals, all the ones and zeros and ones and zeros and ones and zeros, are placed on the wire and transmitted across the network. Then we have the layer 2 or the network layer, where our protocol data unit is called a frame. These are where the Ethernet and the MAC addresses are held. Then we have our layer 3, which is our network address here, a network layer rather. And the PD uses packets. And this is where you've got your IPv4, your IPv6, your ARP, your Internet Control Messaging Protocol or ICMP also reside. Then we have our layer 4, which is our transport layer, and our PDU is segments, and this is predominantly where you find TCP or Transmission Control Protocol and UDP, which is the datagram protocol. Now, you find a lot of the time in networking when data is being transmitted, people just say packets. Well, packets is a layer 3 protocol here. However, a lot of the time people use it interchangeably. It's not correct, but we all do it. And the first 4 layers from here to here is generally what you're interested in as a network engineer. So layers 5 is your session layer, and the PDU is data. These hold things like SQLs, remote procedure calls, secure copy protocols, SIP. Layer 6 is your presentation protocol, and the PDU is again also data. You find things like file compression. You think if you're using things like 7-zip or WinZip, they run on this particular layer. Encryption protocols and things like JPEGs, MPEGs, and SSL. And layer 7, which is the top layer, is the application layer, and the PDU here is again data, and this is where you find the likes of HTTP, HTTPS, file transfer protocol, POP3, and SNMP. If we have a little look at the 5 layers of the TCP/IP model, it's very similar. We have our physical layer here, and again the PDU is in bits. We have our data link layer, and the PDU is frames, so this is still layer 2 for Ethernet. We have our network layer, which is our layer 3 layer, and our PDU again is still packets. It performs the exact same function as the OSI model, layer 3. We then have our transport layer, which is our layer 4, and the PDU again is segments on here, and this is where the TCP and UDP resides. However, the application layer or layer 5 right here, this is where, compared to the OSI model where the top 3 layers are, these have all been condensed into one. Okay, let's just have a little look at a couple of similarities and a bit of information about each model. So with the OSI model, we can see that it's been developed by the Open Standards Organization right there. We can also see that the OSI model provides clear distinction between interfaces, services, and protocols. The OSI model refers to Open Systems Interconnection. It also uses network layer to define routing standards and protocols, and the OSI follows a vertical approach. So basically, you start from layer 1 and go all the way up. It's developed by the ISO organization and it has 7 layers. In contrast, the TCP/IP model was developed by ARPANET, and that was designed prior to the internet. It was devised by and used by the US military. TCP/IP doesn't have any clear distinguishing points between its services, interfaces, or protocols. If you remember from the last slide, the top 3 protocols that would layers rather that would be in the OSI model have been condensed into one. TCP also refers to transmission control protocols, but you do get that in both. And TCP and IP only use the internet layer on the TCP model. Okay, there's some advantages here of using each particular sort of model. I mean, the most predominant model in use today is the TCP/IP model, but there are many advantages because it's not just people who develop networking that use these models. It's people that are developing applications that are running on PCs, applications that are running on your smartphone, and they need to know where everything should be sitting. So it's like a standardized approach. So one of the advantages of the OSI model is it helps to standardize routers, switches, motherboards, and other devices, and it reduces the complexity and by standardizing interfaces, so people know when they're using this model exactly where they should actually be. Okay, it also facilitates modular engineering. Now these are all interlinked with each other. Now, the OSI model was also standard model in computer networking itself. There are some disadvantages to using the model, though. Trying to fit protocols in can be a little bit of a tedious task, and you can only use it as a reference model because TCP IP is the predominant protocol at the moment. So it doesn't, apparently it doesn't define any specific protocol. So most things can be used, but it's not designed specifically for the OSI, which means that sometimes where there's some interoperability, it can be a bit of a problem. Okay, let's have a little look at some TCP/IP advantages. So it operates independently of the operating system. So it doesn't matter whether you're using, let's say, a PC or a Mac or an iPhone. Excuse my handwriting, is terrible. So because it works independently, it doesn't make no difference what operating system you're doing. The model just completely works. It does support virtually all routing protocols, the likes of RIP, OSPF, IS to IS. That says 5, but that's an S. TCP/IP model is highly scalable. So it's a good for client-server architecture. So there's always a lot of back and forth between the client and the server that is synchronized with the TCP/IP model. And you can also use it to establish connection between 2 computers. So you have one PC on your desk and you have another PC next to it. They will communicate using the TCP/IP model, absolutely no problem. There is some disadvantages of the TCP/IP model. It's a complicated model to set up and manage. Replacing protocols in TCP/IP is basically not very easy. And another thing that you may come across is that when you're network troubleshooting, because the top 3 layers in the OSI model have been split into 3, it makes it a lot easier to determine at what layer the actual issue you may be having is located and therefore have it resolved. But again, as a network engineer, however, you generally won't be dealing with that. You'll be dealing with layers 1 to 4 generally only. It's normally the system admins who will be dealing with things that are running in layers 5 to 7. So let's have a little look at some encapsulation. This is basically every single packet that is sent has to be encapsulated and it follows the same format. So in this example, let's say we're going to the BBC. First thing that happens is your PC is going to generate a request, generate some data. And then what's going to happen is that's going to move down the stack of your PC, and then eventually it's going to get to the transport layer where a TCP header is going to be placed on it. Once the TCP header has been placed, it's going to move down to the next layer, which is a network layer, and then an IP header is going to be placed over that packet. Then once that's been happened, it's going to go down to layer 2, and then you're going to have the MAC address header put on it, and the frame check sequence will also put on the end of the packet. You notice how I use the word packet. It's not a packet, it's actually a frame, but as I was saying earlier, people just use it interchangeably. And once every layer has been encapsulated, it then gets converted into binary ones and zeros, and it gets sent off on the physical cabling on your layer 1. And when it reaches the other side, the exact thing happens again in reverse. This layer is stripped off, then the IP header is stripped off, then the TCP header is stripped off, and then all you're left with is a packet of data, and then your system will then know what to do with that. Let's say, if I'm saying it would display a web page. We'll have a little look at this. I've got some Wireshark captures here of a transmission between BBC and one of my machines. So as you can see here, in this Wireshark capture, we have our 5 TCP/IP layers. So we have our layer 1, our transport layer, we have our layer 2, we have our layer 3, we have layer 4, and we have our layer 5. Let's have a little look into each of them and have a little look. Well, we're not going to look into layer 1 because the layer 1 is just going to be a load of numbers, ones and zeros. But let's have a look at layer 2. So the Ethernet header, as you can see, it has a source MAC address and it has a destination MAC address as well. So if we can look up here, the source 212.58.233 and .254, this is actually bbc.co.uk. Put a C there. Okay, so this is a packet that's been captured coming back to my machine, and this is the IP address of my remote PC. So as we can see, the MAC addresses are there. So this particular frame has come in. It's on ones and zeros there. It's been encapsulated. It's got its layer 2. Then we move into the layer 3 part of the packet, which is the Internet Protocol here. We're using IPv4, which is what we expected. And now, because this is layer 3, we now see the IP addresses are part of this. So the source is that IP address, destination is that IP address, which is me. Compared that to the previous slide where the source and destinations were the MAC addresses at layer 2. At layer 3, the source and destination is the actual IP addresses right there and there. So if we go into layer 4, which is a transmission control protocol, we can now see that this is running on port 80. So that's the BBC is sending us a HTTP packet. It's been sent to this port here. Now this is what's called an ephemeral port. So it would have meant that when my machine requested to get a web page from the BBC, it just used any random port over 1024, and to keep everything separate, it will listen on that port. So the BBC's turned around and goes, oh, I'm going to send it back, and this is the port number that is destined to, which allows you to then have multiple streams going at the same time. And lastly, we have our layer 5, the application layer. That's got has all the data in it. So this will be there's a little bit more further down. I've had to cut it off, but this will contain things like the data that's needed to display the actual web page. So while this has only just been a brief overview of the TCP/IP model, if you work through the actual layers, you'll see how every packet is built together, and especially the encapsulation part of it. We'll cover more of this as time goes by. I hope you've enjoyed this, and if you have any issues, send us a message.